Hello, students. It's Miss Stryker here. I'm getting ready to do a little review of electrostatics. I hope that over the last 2 weeks you had a chance to read Chapter 32, had a chance to not only complete the worksheet, but also upload it onto Google Classroom, that you answered the yellow box questions, and that you watched my little Ed puzzle videos and hopefully did some calculations on your own along with me, having to do with Coulomb's law. So I would like to review electrostatics before I give you a quiz today, and I will give you a half-hour quiz. It is already uploaded for you. And so once we finish this, you can go ahead and take that quiz. All right. I'm going to post this review sheet on Google Classroom. So if you would like to use it to follow along with me and write down, you're more than welcome to do that. And if you don't want to download it or use it at all, that's fine too. It'll be there for you. And so at this point, I'm going to get rid of my face and fill in this template so that we can review electrostatics. And so electrostatics has to do with charges, positive charges, negative charges. Where do they live? They live in matter. Electrons are negatively charged, protons are positively charged, and we know the big rule is that like charges repel and unlike charges attract. So we could charge something up by adding electrons or by taking away electrons, but we can never add protons. We never add positive charge to an object. And so when an object is positively charged, that means it has lost some of its electrons. It has lost electrons. Okay, so you need to know that conceptually, that positive charge comes from losing electrons. Similarly, negative charge comes from gaining electrons. It's never the protons that move. It's always the electrons. A couple of different ways to charge something up. So you can charge by conduction. Conduction just means touching. Okay, you can charge by touching. So you saw that when you take that balloon and you rub it on the sweater. If you watch the FET video, the balloon got very negatively charged. And that happened because it was rubbed against the sweater, right? And so there was some friction going on. And that friction or that touching caused some of those electrons to wipe off onto the balloon, all right? So charging by conduction is touching. Charging by induction is not touching, not touching. So you saw that in the FET video as well. If you took that balloon and you hold it next to a wall, but you don't allow it to touch the wall, so there's some space there. It's not touching the wall. Well, what happens? The wall is full of charges. Actually, it's full of atoms, and each atom has charges in it. So these are all atoms. What happens to the wall when I bring a negatively charged balloon near it? Well, the negative charges in each of those atoms move away. And if the negative charge moves away, that leaves the positively charged nucleus closer to the balloon. This is called charging by induction. So it's always true that a charged object like the balloon will attract to a neutral object like the wall because it causes the atoms in the wall to shift a little bit. Their negative charge moves away, leaving the positive charge close by. That is induction. In fact, when this charge separation happens, the word for charge separation is polarization. Those charges become polarized. All right. So that's what that means. There's a great video showing charging an electroscope by induction. And I'm going to post this link and hopefully you will watch that. But basically, if you have an electroscope or if you have a big conducting sphere, not an electroscope, a big conducting sphere, like the Van de Graaff generator. So this is made of metal, right? And on metal, the electrons are free to move around. If you take a positively charged or negatively charged rod and you hold it nearby, something's going to happen on the conductor. And so let's say we've got a negatively charged rod. let's say we rub this plastic on the sweater, it picks up a negative charge, and now I'm going to hold it next to this neutral conductor. Well, this conducting sphere is full of positive charges and negative charges, but because it's a conductor, the negative charges actually can move away from that rod, leaving the positive charge closer to it. Okay, so that's what happens, charging by induction. Then if you bring your finger over here and you touch this, here's my finger. I don't know, this is my hand. This is going to be a really bad drawing. Here's my head, here's my other hand, and here I am touching the ground with my feet. I guess I have a really long torso. My finger is touching the conducting sphere on the negative side. Well, since I'm touching the ground, all of these little electrons have a chance to travel straight down to the ground. That's called grounding. And that will leave that conducting sphere with a net positive charge. So this video will show you that in action. I will post a link for this video so you can take a look at it. So that'll be on Google Classroom. All right, that's what you're going to see on that video. Last but not least, I want to do a couple of calculations. I want to calculate the force of attraction, and I want to then compare it to gravity. So I'm going to calculate the force of attraction in the hydrogen atom due to both Coulomb's law and due to Newton's law of gravity. So I'm going to calculate that attractive force using two different force formulas, and then I'm going to compare them. All right. And so Coulomb's law looks like this. K Q1 Q2 over distance squared. And remember Newton's law, the gravitational force is big G M1 M2 divided by d squared. Again, in a hydrogen atom, got a positive charge in the middle and a negative charge flying around the outside. Why am I using hydrogen? There's so many elements. Why would I pick hydrogen? It's the simplest one. Okay, it's the simplest element. That's why I'm picking it. I could do this with any other atom. I'm going to use hydrogen because it's easy. So I've got an electron here and I've got a proton here, and I know that they're going to attract to each other with both an electrostatic force and a gravitational force, and I would like to compare the size of each. So first I need to write down some facts. The mass of the electron, 9.11 times 10 to the negative 31 kilograms. The charge of an electron is 1.6 times 10 to the negative 19 coulombs, and it is negative. It's a negatively charged particle, but the size of the charge is 1.6 times 10 to the negative 19 coulombs. What about the proton? The mass of the proton, much bigger, 1.67 times 10 to the negative 27 kilograms. And the charge of the proton is the same as the charge of the electron. It's just positive. All right, so I need those facts. You don't have to memorize those. The only reason you would use those is if you were doing some physics or some chemistry. All right, and you can certainly look them up or leave them in your notebook. You might have to do a calculation on the quiz, and so it's fine if you have your notes open. All right, so what I'd like to do again is calculate the electrostatic force, and then I'm going to calculate the force of gravity, and I would like to compare them. All right, so have your calculator ready. Electrostatic force looks like this, K Q1 Q2 divided by the distance squared. Plugging in 9 times 10 to the 9. There's K. Charge of the electron, 1.6 times 10 to the negative 19. Charge of the proton is the same, so I'm going to square that and divide by the distance between those two things squared. Well, I didn't write down the distance. The distance between the proton and the electron in the hydrogen atom is 5.2 times 10 to the negative 11 meters. So they're really close together. 5.2 times 10 to the negative 11, and I'm going to square that. So now I take my calculator and I'm going to do that calculation. You can pause the video. Be a really good idea for you to pause the video and do the calculation and then make sure it matches mine. So 9 times 10 to the 9 times 1.6 times 10 to the negative 19 then I'm going to divide that by 5.2 times 10 to the negative 11, and I have to square that. Okay, so I get an electrostatic force 8.5 times 10 to the negative 8 newtons. So that's pretty small. All right. How much bigger is it than the force of gravity? How much bigger is it than gravity? So we know how to calculate the attractive force due to gravity. It's big G times the mass of an electron times the mass of the proton divided by the distance squared. Big G, if you remember, 6.67 times 10 to the negative 11. So now I need the mass of electron, 9.1 times 10 to the negative 31. Mass of the proton, 1.67 times 10 to the negative 27. And divide by the same distance, 5.2 times 10 to the negative 11. And I have to square that. All right, so here we go. Pause the video, calculate this out, make sure you get the same answer that I do. 6.67 times 10 to the negative 11 times 9.1 times 10 to the negative 31 times 1.67 times 10 to the negative 27. Divide that by the quantity, 5.2 times 10 to the negative 11 squared. Okay, I get a really small number, 3.74 times 10 to the, holy moly, negative 47. That is so small. Okay, so I could definitely say the electrostatic force is bigger than the force of gravity. How much bigger? How much bigger is the electrostatic force of attraction compared to the gravitational attraction? How much bigger? Well, the way to find that is just to divide them. Fe divided by Fg will tell me how much times bigger it is. How many times bigger? And so I'm going to do that. 8.5 times 10 to the negative 8. Negative 8 divide by 3.75 times 10 to the negative 47. Let's try it out. 8.5 times 10 to the negative 8 divide by 3.75 times 10 to the negative 47. Holy moly. 2.3 times 10 to the 39 times. 2.3 times 10 to the 39. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. That's how much bigger the electrostatic force is compared with the force of gravity. So when I drew my picture up here, I only drew the electrostatic force. That doesn't mean there is no force of gravity. It just means it's so much smaller that I can pretty much ignore it. All right, so that's a little review of electrostatics. We're going to go on to electric current next. Your homework assignment will have to do with the next chapters in your textbook. I hope you had a great week last week, and I hope that your day today is also wonderful. I miss you all. I miss being in school. Good luck with your quiz. I'll talk to you soon. Bye.